Example 1 in 1.3, as you might guess, deals with a geometric sequence, and it talks about doubling bacteria, and this is pretty typical. I mean, it doesn't have to be bacteria. Any living organism, if we look at a long enough, period, is eventually going to double. Now, I guess I shouldn't really say that, because in reality, it's more complex with birth rates and death rates and stuff like that. But the bottom line is that these bacteria are doubling. So it says that 10 bacteria were originally present in a bacteria sample. So I think pretty logically that is going to be our term 1. And then what we're going to look for, I think we'll maybe just do 4 terms here. So term 1, term 2, term 3, and then finally term 4. Well, if the bacteria are doubling, then to go from term 1 to term 2, I'm going to double it. I'm going to multiply by 2. Well, 10 times 2 is 20. Now, if I just gave you the numbers 10 and 20 and told you that it's a sequence, you could approach that as a geometric sequence with a common ratio of 2, or an arithmetic sequence with a common difference of 10. And it's really important that 2 numbers are usually not enough to find the kind of pattern that's happening here. But if we recognize, and this is certainly geometric, then when we double again, I get that term 3 is 40 and term 4 is 80. Now, having these numbers, you should and you need to be able to tell whether this is geometric or arithmetic. And the best way of telling it, I'm going to do the wrong one first, that if I treated this as arithmetic, here my common difference is 10, here my common difference is 20, and here my common difference is 40. The common difference needs to be just that, common. So because we can see that we're adding different amounts as we go through this sequence, it is definitely not arithmetic. But if I look at this as geometric, so thinking about multiplication instead, I'm just going to write that we could say that R is term 2 over term 1, or term 3 over term 2, or, and I'll just do the 4 that I wrote here, term 4 over term 3. And what we should see happening is that if this is truly geometric, these yield the exact same number again and again. So R should be whatever 20 over 10 is, or what 40 over 20 is, or what 80 over 40 is. So just each term divided by the term before it. Well, 20 divided by 10 is 2, 40 divided by 20 is 2, and 80 divided by 40 is 2. So in this particular geometric sequence, we see that term 1 is 10, the original amount of bacteria, and the common ratio is 2. They're doubling. Now, what this would allow me to do is I could say that Tn, which is term 1 times r to the power of n minus 1, for these bacteria, Tn would be 10 times 2 to the power of n minus 1. And if I wanted to know how many bacteria there were after, 60 different doubling cycles have happened, I could put 60 in for n and find the 60th term without actually multiplying by 2 60 times. And just like the first half of chapter 1, the power here is that we could quickly predict how much bacteria there would be in the future without actually having to calculate each and every moment in time, which is a really big advantage.